I teach honors physics at East Hall High School, and today we're going to do a demonstration for collisions. I have my students that are going to simulate different kinds of elastic, inelastic, and perfectly inelastic collisions using giant rubber balls, I guess. I want to say beach balls. So using giant bouncy balls as kind of like a elastic device to allow them to bounce off each other, or by tackling to simulate a perfectly inelastic collision. So we'll see what fun thing. So we talked about a bunch of different kinds of collisions already. We've looked at the changes in momentum. We've looked at whether momentum's conserved in all the different kinds of reactions. And we also looked at the conservation of kinetic energy. What kind of reactions is momentum conserved in? Or not reactions, collisions. All three, right? What are those three? Inelastic, elastic, and perfectly inelastic. What are most collisions in real life?
Inelastic.
Just regular old inelastic, right? So they collide, they deform a little bit. What's not conserved for inelastic?
Kinetic energy.
Momentum is. Kinetic energy is not.
Yeah.
Okay, is kinetic energy conserved for perfectly inelastic collision?
No.
No. What's a perfectly inelastic collision?
Isn't it mold together?
Yeah, you got two objects at first, they collide, and they are one object at the end, or one mass, right? Okay. Then for elastic collisions, what besides momentum is conserved? Kinetic energy. And what's an elastic collision?
Like two cool balls hitting each other. It's when they exactly bounce off each other.
So two objects hit each other, they stay separate after the collision, right? And also they are not deformed. So they return to their original shape. That elasticity, you think of that way, as it returns to its original shape. So we're gonna just simulate a few collisions. I've got chemistry terms stuck in my head. All right. So we're gonna simulate a few collisions. I'm gonna let the audience decide which type of collision we want to do first.
Inelastic.
You want to do an inelastic collision?
Inelastic.
So we want things to, well, maybe I don't want their bodies to break. So we're not going to do
Elastic.
So we'll do an elastic collision that's technically inelastic, right? So what should the two objects before the reaction look like? They should be two separate two separate objects, just like they are now. What should they look like after? The same, but technically a little bit deformed, right?
Yeah, you better get deformed.
Okay. So, how do we want to set this up? Y'all, we need the scenario. Do we want one object still, the other object moving? Do we want them both moving? Do we want them both at rest initially and they push off?
Jake at a standstill.
Jake stands still, Leslie runs.
You want Jake standing and Leslie running?
Let's go!
Let's go!
Jake, you guys move yourself.
Okay, so Jake, I'm going to have you stand in the middle circle.
Woo!
Leslie.
Go, Leslie! Go, Leslie!
So you're going to stand in the middle circle. That way you stand in the middle.
Hey, Leslie, hit him with that good.
Okay, Jake, you want to stand your ground?
Jake, you better stand in the middle. Jake, take charge.
Yeah, use the balls because it'll be more fun because you can bounce off a little easier. Come on.
Jake, sit.
We're doing elastic, right?
Hold
We're
it in
not
front of
doing
your
fantastic.
chest, son.
We're not doing perfectly inelastic. We're doing elastic. So you should bounce off. Start in the middle of your circle. That way you got it. There you go. Okay, everybody. 3, 2, 1, go. That should have been elastic, right? As like an ideal scenario. So yes, it should be math-wise, but in real life, those balls do, contract a little bit. We do have some elasticity there, so in real life, kinetic energy and momentum technically are not conserved. Why would momentum not technically be conserved in this case? What's the one thing that says that momentum is not conserved? Friction. Did they experience some friction?
Yeah.
Yeah, especially like whenever their clothes ran up against each other. Right, they both have friction by their foot on the ground. Okay? Alright, so let's try another elastic collision, or inelastic. But this time I want them to hold your balls like in front of you so that way the balls hit each other. Okay? So go ahead and we'll try that again. We'll count 3, 2, 1, okay? Y'all ready? You guys set up? Okay. So on the count of 3, everybody. 1, 2, 3.
Wait, do I run to him or do we
No,
both
you
run?
run to him. It's the same thing. I just we're gonna hold the ball to the front now. We'll see another thing here in a second. So this one worked a little bit better. What did you notice about the two objects at the end? So they bounce off each other. Did they end up going different directions? Yes. Ah, okay. So this time, the two objects, they didn't brush against each other and go past like they did the first time. Now, gentlemen, now we had two objects that run towards each other, or one object going towards the stationary, and they go opposite directions. Okay? In that case, go ahead. The same velocity? So should they go the same velocity at the end? Same speed?
Momentum.
Momentum! Okay, so what says that at the end of the reaction, or at the end of the collision, I keep saying chemistry terms, what says at the end of the collision that they should each have equal and opposite momentum? Conservation of momentum. Okay, so if they have the same momentum, who do you think has a higher mass? Say Jake, because women always like to have the lower mass. Come on. Alright, so if Jake has the higher mass, should he be propelled backwards as fast or as far as Leslie was? No, she should have a higher velocity backwards, shouldn't she? So what's the relationship between mass and velocity if we're looking at momentum? Are they directly related or are they inversely related? Inverse, right? Like if one's bigger, the other one has to be smaller? Okay. So do y'all want to try one where they both run towards each other? Yeah. Yeah? Okay. So Jake's going to start.